Myself, Dhanyashri. Our topic is logical and bitwise operations. I'm here to explain about introduction. Assembly language programming provides a way to write instructions that closely correspond to the actual operations performed by the CPU. It allows direct manipulation of data stored in register and memory, making it ideal for controlling hardware and performing low-level operations in microcontrollers. Logical and bitwise operations are fundamental to embedded system because they allow the processor to test, combine or modify individual bits of data. These operations are widely used for tasks such as sensor monitoring, flag checking, and control logic implementation. For example, using AND, XOR, or operations, a microcontroller can detect common sensor activations, combined status, or difference between two sensor inputs. Through this experiment, we understand how to efficiently use logical instructions to process sensor data, optimize memory usage, and perform decision making at the bit level, skills essential for real time embedded system design.
Hello everyone, I am Adira. I am explaining now abstract. This will demonstrate the logical and bitwise operations using 8051 microcontroller. It implements AND or XOR and even not checking on sensor status bytes, utilizing direct addressing for efficient memory access and data handling. The program execution and results were verified through Keel microvision simulation, strengthening the understanding of the bit level operations in embedded systems. The experiment highlights the importance of low-level programming and hardware interaction in microcontroller-based applications. It also provides practical insight into optimizing performance and accuracy in embedded control systems. Next, the output will be explained by Lasya.
Hello everyone, this is Lasya Pishetti. I will now be demonstrating the bitwise operations within the Keel Microvision IDE. Our focus today is on observing the precise results when specific data is manipulated in CPU registers and memory. The demonstration begins by ensuring the source file bitwise is correctly integrated into the project. This is critical step for any assembly project. Adding a new source file. We navigate to target 1 source group 1, right click and select add new item to group. Selecting the type, we select ACM file and name it bitwise. File creation, adding opens the new assembly file window ready for code entry. The assembly code we are using, which is now visible in the Bitwise tab, covers 4 key areas. The core of the demonstration is the simulation accessed via debug, start or stop debug session, simulation environment. Clicking OK on the evaluation mode, message opens the debugger. We can see the registers window on the left and the memory window on the right. Memory initialization, we manually edit the memory location 0x40 as 18H and 0x41 as 7EH for the first block of instruction, which is crucial for testing the initial state of the registers. Execution and observation, using the step F11 command, we advance the code. For running the full code, we click run to execute the rest of the program, including the even or odd check. Final result check, the program halts the infinite loop SJMP, the final memory state which stores the result of the even or odd check can be examined, and disassembly window shows the full instruction set. The simulation confirms that bitwise operation provides the immediate low-level control necessary to manipulate data precisely at the bit level, which is the cornerstone of embedded programming. Bitwise AND, when the assembly code executes the AND operation, it checks for common active bits between 18H and 7EH. The simulation shows the result stored in memory is 18H. This means the only bit set in the results are those that were active in both sensor readings. Bitwise OR, execute the OR operation, combines all active bits from both inputs. The memory update confirms the result is 7EH. Bitwise XOR, the XOR operation identifies bits that are different between the two inputs. The simulation shows the result of 18H XOR 7EH is 16H. As we step through the instructions, the debugger confirms these precise results are loaded into their respective memory locations. The final section demonstrates the highly efficient even or odd check, we use the XOR result 66H as our input data. The code executes an AND operation between 66H and 01H to isolate the least significant bit. The LSB of 66H is 0, therefore, the operation results is 00H. The simulation confirms that 00H is stored in the result address. Since a 0 result signifies that the LSB was 0, this confirms the sensor reading of 66H is even. This successfully validates all the bitwise logic and data manipulation for this embedded application.
Hello everyone, I am Siri. Now I tell about conclusion for this topic. This experiment successfully demonstrate how logical and bitwise operation like AND or XOR and even odd detection work on sensor data, and it helped us understand accumulator, user, flag checking and memory addressing, given practical knowledge of how microcontroller make real-time logical discussion. Overall, it built a strong foundation for advanced and sensor-based applications. Thank you.